All right, folks, welcome everyone to the MIT Robotics Seminar. This is the first seminar of the semester, so I'm excited to have you here. And we have a great speaker to kick off the seminar series this semester, Aaron Dollar. Professor Dollar is a professor in mechanical engineering and material science and computer science at Yale University. And he's also a research lead at the Boston Dynamics AI Institute. He got his PhD from Harvard University and was actually here as a postdoc at MIT working in health sciences and technology and the MIT Media Lab. So Professor Dollar is the recipient of many awards, including Young Investigator Award from AFOSR, DARPA, NASA, NSF. It's a long list. And he's also the founder of the IEEE Technical Committee on Mechanisms and Design. And besides co-authoring more than 200 papers and mentoring more than 40 PhD students and postdocs, he had an incredible impact on the community through the release of the YCB manipulation benchmarks, which many of us have used, the Yale Open Hand project, and the spin-off company Right Hand Robotics, among other things. He's also a fellow of the IEEE, and it's a huge pleasure to have him as a speaker today. Before leaving him to his talk, just a reminder that you have a small social event after the seminar, so join us, it's over there. And I also wanted to thank our sponsors, which are making this seminar possible. This year, we have an amazing lineup of sponsors, being Amazon Robotics, Skydio, and Symbotic. Okay? So Aaron, thanks for being here. Take it away.
Thank you. Pulkit, I did not know you were going to have to go like far away to get coffee. I casually mentioned Pulkit that I needed my afternoon hit of coffee, and apparently he had to go. All right. Well, thanks for everyone coming. Thank you for the coffee. Yeah, it's funny. You put together these bios, and it's like you want to list things, and then you get embarrassed that when somebody has to read through your accolades in front of you. So, anyways, thank you, Luca, and thanks for inviting me and coming. As Luca implied, I come from a mechanical engineering background, which there are some of us in the robotics community. We are a minority, and that's kind of why I started the technical committee on mechanisms and design to sort of, let us come together and establish a little bit more of a presence in the community and so forth. But we know that robots are inherently physical, and so there's a lot of really interesting inherently physical problems. And I think on manipulation is probably the most interesting, at least, I'm biased, I guess, but it's really where the rubber meets the road in terms of dealing with the real physics and constraints that come from it that makes stuff especially challenging. So I'm mostly going to talk today about how different design approaches, and in particular the under-actuated mechanisms that I do in the lab, can really help deal with this problem, and really coming at it from a low level. I'm very much a bottom-up minimalist kind of guy, and so pretty much everything I'm going to tell you about is done to the extent possible open loop and feed forward. We really try to find mechanical solutions that just work passively as well as possible, and then we think after that about what needs to be added to kind of completely integrate them into a functional system. So yeah, I've been working almost exclusively on mechanical designs, and I'm going to talk only about the hand stuff, but we do a few other things in the lab. I'm just going to start by talking about why I think manipulation is so challenging, and this sort of is to lay some groundwork for where I'm coming at this from, but maybe it will also be educational for you as well. So if you think about most of our robotic systems, right, we put an actuator on every joint, and we can move them around in free space with no issue. If you imagine this here, this three-link a serial chain as a finger or an arm moving around, imagine there's a joint at all of the three links, no problem. The challenge really begins when you make contact, and the contact adds constraints. And I like this example because it should kind of hammer home a little bit the situation. It's exaggerated to an extent, but when you make contact with that fingertip, that contact is going to impart some kind of, some kinds of constraints to the system. It won't be a complete joint like that, but it might functionally be a complete joint. But the real issue here is that in free space, that 3-link manipulator has 3 degrees of freedom. But as soon as you make contact and establish that other joint or that other constraint there, it goes to a 4-bar linkage, which has 1 degree of freedom. So all of a sudden you had 3 actuators, acting happily in free space, and now you have 3 actuators trying to control a 1 degree of freedom kinematic system, and you're inherently, however you want to think about it, over-constrained, redundant. It's a challenge, okay? And especially it's a challenge because most of our actuators, to be practical, have to be highly geared and so forth, and that makes them mostly position sources, which are especially sensitive to this kind of over-constraint. So what can you do about it? Well, there's a lot of challenges that I mentioned. Impedance and torque control is really kind of the typical way that you would want to deal with this. It requires some way to sense forces or torques, and then dealing with it. There's all kinds of challenges dealing with backlash and other kinds of things as well. But it definitely helps. In highly controlled environments, this is not as big of an issue, but in unstructured environments where there's a lot of uncertainty is where this becomes especially challenging. Okay, so there might be a solution to deal with this. There is a solution in that case, but you might not know what that solution is in order to make it actually work. All right. So essentially, where I come at this from is instead of thinking about this in a control sense or other kind of sense, can you just deal with this from the bottom up from a design approach? And you know probably that compliance can help, and we already talked about how impedance control can help. It basically adds some springiness to the system, and that springiness allows some amount of kind of passive reconfiguration. And here I just put a couple of examples where, we, on the left at least, we know that compliance can help, help with vibration control from a hammer. If you didn't have springs in your car, it would be a very bumpy ride and so forth. People have taken this to extremes of having inflatable robots. That's Chris Atkinson in a Baymax suit there. But I actually started on this project when I started my PhD. I was on a Navy Muri where we were working with Bob Full, who was a cockroach biologist. That's a cockroach on the bottom going over a rough terrain. And Bob's work at the time essentially showed that cockroaches can go over these extremely rough terrains essentially open loop, that they're adapting to the terrain much faster than their closed loop control system could actually impart. And so it must have been the springiness in the joints of the cockroach that allows it to go over these rough terrains super fast. And I should find a video that shows this, but the cockroach is running like crazy over these. And so there were some cockroach-inspired robots. You might know Rex. I was involved in the one that produced Sparlita. But so compliance can help. But what can help even more is essentially differential transmissions. And I'll use the example of a car differential, and just so everybody's on the same page, your car has a single motor usually. Now with electric cars, it's not quite the same anymore. But you have a single input from the engine, and you want to route it to your wheels. If it's a two-wheel drive, which is the typical situation, you would need to route that single input into two different wheel outputs. And if the coupling was rigid, essentially the wheels would always spin at the same rate, and that's fine when you're going straight. But if you're going around a curve, the outer wheel has to spin at a faster velocity than the inner wheel. Now, if you were a roboticist, you might say, okay, well, I just need to sense the curve of the road and then actively control the wheels in order to make it spin. But you can find a mechanical solution to this, and that's where the differential came in, where there's essentially a mechanism that has an extra degree of freedom. And that degree of freedom is essentially passively specified or passively controlled by the shape of the road. And you might also know this if you've ever gotten into an unfortunate situation where one of your wheels is off the ground. You're not going to go at all because that other wheel has to actually be constrained by the road in order to apply torque. So if both of the wheels aren't in contact with the ground, you actually don't apply any torque because you have this extra degree of freedom that needs to be immobilized by that contact. So this is really a brilliant design. It's been the standard for 100 years now, essentially, in cars. And these differentials are what we call underactuated mechanisms. And underactuated, comes from the sense that you have fewer actuators than degrees of freedom of the mechanism. The term underactuated is used in a lot of other senses as well, like in a control sense. But for us, we're talking about it from a mechanism standpoint, which is, you can think about it as differentials. And both compliance, mechanical compliance, which is springs, and differentials add degrees of freedom to the system to help deal with this overconstraint, right? So you're really not dealing with the overconstraint directly. You're basically adding more degrees of freedom so you're not overconstrained. And when you're talking about springiness, whether it's impedance control or mechanical springs, you have this constraint of F equals Kx, or however you want to think about it. And that can be fine in certain situations, but in other situations it can be problematic. Either way, it's some kind of additional constraint. With differentials, they can essentially be completely unconstrained. There's friction in the mechanism, which adds some constraints, but you can get adaptability without that F equals Kx relationship, and also get a lot bigger ranges of motions and things like that, right? Your car differential essentially has an infinite amount of range of motion that it can handle. So the approach that I've been taking essentially is to incorporate these kinds of mechanical features in order to deal with these kinds of real-world contact issues that are highly problematic, especially in robot manipulation, and do it in a way that essentially is passive, like purely passive. And I started using the term mechanical intelligence. There are other people that use similar type terms now. Basically, this is trying to get computer scientists to appreciate the value of mechanical design, but it's basically good mechanical design, right? And the idea is essentially to prioritize the open loop performance first and incorporate some of these nifty mechanisms. And like I said, do it from a bottom up. Only really go to the point where you need additional sensing and control if it's absolutely necessary. We always need high level perception, but it's mechanism first, essentially. Okay. So one of the issues with underactuated mechanisms is if you go back to that example of the finger moving in free space, to make that so that it's not over-constrained at contact, you have to have it be under-constrained before contact. And that's kind of where the challenge really lies in designing these things is you can always add just purely passive joints, but as soon as that constraint is removed, they're just going to flop over and not be able to support even their own weight. So you need to be able to apply torques to all of those degrees of freedom, and that's really where the challenge lies in actuating these things and coming up with mechanical solutions. So you have to start off being under-constrained before contact, and we do use a lot of springs in order to have the robot keep its shape before contact, right? You try to keep them as soft as possible, but you have to deal with gravity and so forth. And so you basically want to kind of loosely couple those degrees of freedom when you're moving in free space so that when you do make contact, that it's fully constrained. All right, so just to kind of put this in a more concrete example, this is the hand that was sort of the product of my PhD work. I did my PhD at Harvard with Rob Howe, and just to kind of break it down, focus on one finger here for a second. There's a single tendon that's anchored on the distal link, and it runs over some pulleys to the base. And those pulleys are designed so that you apply torque to both of the joints of the finger, okay? And it moves just freely over here, so this is sort of like a free spinning pulleys. And essentially when I pull this tendon, both joints move. There's some springs there that keep it in its default configuration. But I pull on this tendon and both move. Now, where this finger is underactuated is if I make contact on this proximal link, I can keep pulling that tendon, and this distal link is going to keep closing until it makes contact. So I can just blindly pull this tendon until it stops moving, And in an ideal world, which is what we try to design for, you're going to make contact on both links. Okay, just pull it till it stops moving, and you make contact. Now, if you build up this pulley differential in this kind of stacked fashion, it allows all the fingers to kind of give or take tendon as needed, right? And you just take this single tendon at the base, and all 8 joints of this hand will continue to close until they make contact and are immobilized. So essentially, it's under constrained, and you just keep pulling this tendon until it becomes fully constrained, and that is when you have sort of a stable grasp. So just to kind of show that here, this is all open loop. We're just running the single actuator to stall, and I'm just putting things in the hand, mostly just to show how it passively adapts to the different shapes of object, different positions of those objects, with the idea that we wanted to optimize not just the range of objects, but also the amount of uncertainty, right? So if you're offset from the center of the object and so forth, it still works. Again, no sensing here whatsoever. We're just running that single actuator to stall. I spent a lot of time designing it, but it just sort of works passively because of this concept. And then here's using it in a little bit more of an interesting setting. I'm teleoperating this. The robot there is set up in just the 3 degree of freedom configuration. So we just have essentially XYZ control of this, and I'm looking at it from the side, and I'm just hitting a button to close the hand whenever I want to. You're seeing benefits not just of the under actuation, but also the mechanical compliance, which is off axis, right? I showed you that planar diagram in the last image. There's a lot of sort of softness off axis here as well, as you can see. So my typical joke here that I would tell, which maybe some of you have heard before, is I would do this activity and it worked great, very robust, reliable. There was a program manager coming through the lab, and my advisor said, "Aaron, show him the demo, right?" And so, busy guy, I'm trying to do it fast and impress him and everything. And the first time I spilled the wine was in front of this guy, and we didn't get the funding, but. Anyways, it works really well. You see that very natural, very compliant interaction. Certainly I'm benefiting from my own perception here, but if you really just focus in on the hand itself, right, it's all essentially open loop. All right, so kind of just to summarize why it works, any of those contacts are going to add constraints. And in a typical robot system that is fully constrained to begin with, you're going to end up being highly over-constrained. And that's essentially because you're going from an open kinematic chain to a closed kinematic chain. And that's just physics. You can't get away from that. It's always going to be the case. And so any of your actuated degrees of freedom, especially because your actuators aren't ideal, they become redundant and you have to sort of precisely co-activate these things. Also, just to give credit where credit's due, if I can get back. So I kind of discovered those under actuation myself just by playing around with things, only to figure out that other smart people have figured this out too. The Barrett hand, which you could even buy when I did my PhD, has an under actuated mechanism in it. It's sort of a clutch type mechanism that decouples degrees of freedom from one another. And then Clement Gozlan at Laval University has really been doing amazing stuff in this area for quite a while. And he's often one step ahead of me. My nemesis now, he's great. So this is actually work that Lyle Odnero did, who's here in the audience. Just to kind of show you how this can be applied to a little bit more different types of situations. Here we designed the fingers and the fingertips to be able to grasp small objects off the table. But you see there's lots of contact with the table here. Let me just replay these things. So you're dealing with the constraint due to the contact with the table, as well as the constraints due to the contact with the key, and then also the closed loop constraints between the fingers once you make those kinds of contact. And we're benefiting here from both the mechanical compliance, the springs in the joints, as well as the under actuated closed loop chain. But just to kind of show you this, most robot videos, you see like the one good take, and you never know like how many hundreds it took to get the one good take. So this is just doing a whole bunch of these things one after another. All that we're doing here, we're sensing the center of those objects and just servoing the robot to that position, and then doing an open loop or feed forward, however you want to think about it, closing of those fingertips, and you can see how robust it is. Yes. Yes. So, all right. So that work was done again with Lyle in context of the DARPA ARM program. We were also working with iRobot, who did a lot of the systems integration, and my advisor's lab, PhD advisor's lab, who did a lot of the sensing as well. This was the hand. It's three fingers, 5 actuators. We designed it so that you could both do sort of a pinch grasp to do kind of those small objects that we looked at before, as well as this power grasp, which is like the first hand that I showed you. And then we have now a version of this that is available open source that has 4 actuators that's otherwise similar, dubbed the Model O after Odhner, who named it after himself. No, just kidding. But we had the original hand we called the Model T, and then we had to find other letters, and so we have now a tradition of naming our hands usually after the person who made them. So, all right, and they started a company. So Lyle and the 2 students are 2 people from Harvard, Right Hand Robotics, and they were selling the reflex hand. What they call it a reflex hand for a while. All right, so what I've showed you there is all grasping. Most of what I've been doing since then has been what you might consider dexterous manipulation, and maybe you consider the pinching of the small objects within hand manipulation also. But this is a much more difficult challenge, but the similar kinds of issues, right? You still have these closed-loop kinematic chains that you can't possibly get away from, and so you have to design these systems so that they're highly under-actuated before grasp. Before the object acquisition, in order to make it work properly. And at some point, I realized that there was this great analogy out there in terms of parallel mechanisms. So if you think about grabbing an object like with your fingertips, which is a lot of where your dexterity comes from, this is 5 parallel, fingers or legs, however you want to think about it, all in contact with this object. And people in the parallel mechanisms community have been for a long time wrestling with this problem of how do you develop effective kinematic architectures that deal with the fact that you have this highly parallel kinematic chain, and you don't want to have the actuators be fighting each other. And so essentially all practical parallel mechanisms out there are exactly constrained. And so what that means is if you think about, so this is a Stewart platform. By the way, the Stewart platform is often used for flight simulators. They'll put a cockpit on it and have hydraulic actuators that move it around. It's 6 degrees of freedom. And then the Delta platform, which you may have seen is a really popular pick-and-place actuator, robot. It's got 3 actuators, and it moves in a strictly XYZ configuration. All of these, the platform or the output, there's exactly as many degrees of freedom as there are actuators, right? So for a 6 degree of freedom parallel platform, there's going to be only 6 actuators, and any more would be redundant, okay? So they have to have some sort of orthogonality to them. And so what happens is if you think about these connections, if this platform moves in 6 degrees of freedom, that means these legs also have to move in 6 degrees of freedom, right? Because they have to track it. So each of these legs or arms, however you want to think about it, have to have 6 degrees of freedom. And if you need 6 total actuators, that means that each of these on average needs to have 1 actuator and 5 passive degrees of freedom. And so that's the case with these ones. There's usually a spherical joint on one end and a universal joint on the other, to add the other 5 degrees of freedom because they all have to move with the platform. Same with the Delta platform. So I started to hire some postdocs from the parallel mechanisms community to start to think about this. And we started to do a little bit of modeling and so forth to actually develop some hands from this. Sorry, I'm just going to go quickly because that was written out versions of all the stuff I just said verbally. But this is what we call the Stewart hand. We essentially use the kinematics of the Stewart platform. It looks like it's 3 fingers here, but we kind of coupled 2 of these actuators each to have sort of 3 fingers. And we basically built a highly dexterous 6-degree of freedom hand that is exactly constrained. And not exactly. There is one additional actuator that opens and closes the fingers, but essentially after that contact is made, that actuator is sort of out of the loop. And so we can grasp objects, manipulate them in 6 degrees of freedom. It's also teleoperated here, but you can see the kind of dexterity. And we have similar ranges of motion as the Stewart platform, so it's a pretty effective mechanism. All right, another cool design. We actually have a new version of this that's even better. This hand has essentially, we call it a spherical hand because there's 3 axes that all intersect the same point in space, which means it's a purely sort of rotational mechanism. And that point is fixed, essentially. So it doesn't matter what you're grasping, you know, from the object standpoint. It doesn't matter where the object is contacted with respect to the hand. You're always going to be rotating the object about that known fixed point in space. And so at first we started to think about this as, you know, just kind of an interesting rotational mechanism, but now we started to think about it as sort of almost like a proxy or an alternative configuration to a wrist, because that's essentially what your wrist does. And wrists are really hard, you know, kinematically, and so the idea of being able to maybe, you know, unify a hand and a wrist together in a single mechanism is kind of promising. This video uses this old configuration, which doesn't have nearly as much range of motion as the new one that we're about to publish soon. Okay, this might be slightly out of order, but I started to think about another way of thinking about these constraints and just the whole problem in general. And if you think about, you know, from a control standpoint, or however you want to think about it, you have all these axes. You know, there's this sort of hyperspace of control variables that you have available to you. And if you want to let's say, command your robot to do something, in these highly actuated situations, you're going to have, let's say, a single point in space that's going to be a valid solution. And in general, with uncertainty in the system, you're going to think that this point over here is the target that you're reaching for when it's actually there in the middle. So this is just kind of to show the difference between traditional, fully actuated, you know, rigid, however you think about that approach. You're always going to be off, and it's always going to break, basically. If you add passive springs or impedance control, you might dilate the volume that you can be in and still have a successful solution to some amount, right? So as long as you're in that volume, if your uncertainty is, you know, limited and so forth, you still might be in an okay situation. Essentially, what underactuated hardware allows is a much bigger range of successful configurations, where as long as you're inside of that volume, you are not going to break it. It's going to, you know, keep a hold of the object, and so forth. So that's good, not just from the standpoint of you know, being able to maximize the amount of allowable uncertainty that you can handle, but it also enables you to do a few other things that I'll show in just a minute. Okay, so just to kind of lay out some of the benefits from this approach, you're generally very robust to uncertainty and error. You have a greatly reduced need for precise sensing, modeling, planning, however you want to think about it. And yeah, let me just show you this here. You can do a lot online blindly, essentially, without dropping it. So I'm going to show you some approaches where we're sort of leveraging the fact that you can just act, you know, essentially blindly within that successful volume and do a lot more with a lot less. This is sped up, by the way. Sorry to disappoint Daniel. This is called the Model Q, I think, which we didn't have a Q in the lab. That was Ray Ma. This hand is specifically designed to do finger gating. So just going back to that before we get to this one, there's a pair of fingers, 2 pairs of fingers that can all grasp and hold the object. And then one of the pairs of fingers has a rotational axis on it as well. And so you can notice that we'll be able to grasp the object, then spin it essentially to be able to regrasp and orient it in a few different ways there. This is just another thing that we can do to kind of leverage the sort of passive adaptability. This is very tight tolerance insertion. So 1/4 of a millimeter clearance here between the objects and the pegs in the holes essentially. And we're leveraging essentially the mechanical compliance and passive adaptability of the thing in order to do that. That was sped up only slightly, Daniel, 3x. But we all have places to be, so, you know. All right. Another thing is that when you're thinking about this from a planning standpoint, your searches can converge much faster because the space of potential successful solutions is much larger. So we did a few things along those lines, and I'm not going to go too much into detail, but we did some sliding examples where you have the table constraint that is a hard constraint on the motion, and trying to find a plan for that to be able to move the object in that plane of the table accurately is very challenging, especially if you assume everything is rigid. And so we really leverage the passive adaptability here to make it a lot faster. So you can kind of get that. The other neat thing that I'm even more excited about is if you have this big volume of successful solutions, you can think about it as sort of like a safety region around where you're at. And you can do all kinds of things knowing that you aren't going to fall over and break, let's say. So you can model and do modeling and estimation online by, let's say, doing exploratory actions in that space and watching what happens or collecting data while you do it. So where is that video? Did I delete that video? Oh no. I have a wonderful video here. It's just that I accidentally deleted. No, but we had this great project that we called Self-ID, where we essentially would blindly manipulate the object. We just have some actuation commands in random directions, and we sort of perceived what happens. And with, in this case, we were using particle filters to come up with some kind of controller, but basically watch what happens due to blind manipulation and sort of learn a controller online in a very effective way. So that was a science robotics paper that came out a couple years ago. If you're interested in our hardware, somebody asked last night, it actually keeps coming up, Ted actually asked last night, how do you make an impact essentially when your work is on hardware design? Because you can write a paper and talk about it, but you can't just allow people to download code necessarily and run it. And so one option is starting a company and selling them, which for research hardware, there's not much of a market. And so that's not a great solution. One alternative is basically we started to even ourselves use 3D printing a lot more because it started to get better and better. And we sort of consciously started to force ourselves to think about designing our hands with purely 3D printed or off-the-shelf parts so that we could share them more easily. So I started the Yale Open Hand project. There's something on the order of like 8 to 10 different hand morphologies out there with modular fingers, and the CAD is out there so that you can modify it as well, and really detailed instructions and videos as to how to do the post-processing steps. We even do a lot of the soft materials through some molding. We at some point we're going to do a non-molding version. I don't think we ever actually got that out, but try it out. Pretty straightforward stuff. Still, we don't support these things, so you have to figure it out yourself. But those use the off-the-shelf Dynamixels and a bunch of other easy off-the-shelf components. We also have a website that aggregates a lot of open hardware projects called the Yale OpenRobotHardware.org. I don't even know how many projects are listed there, but there's a bunch. Just a quick plug, my most recent PhD graduate who did his PhD was designing a prosthetic hand. He happened to graduate and do a topic that was extremely timely, got hired by Tesla to work on the Tesla bot, and this is not letting me forward. Sorry, I don't have a video control bar here, so let me see if I can. All right. Elon is muted, but that's a good thing. Sorry if there's any Musk fans out there. So this is the Tesla bot, and those hands that were behind him are the hands that my student Mike ended up designing, and they're somewhere in here where it starts looking at the actual hands. Not incredibly impressive performance, but it was impressive that they did it so quickly. It was only like a year and a half or something here. So that's Mike there talking about his biologically inspired hand design. Anyways, I had no idea. I mean, I knew he got hired for Tesla. He was like one of the only people that worked on this, as far as I understand. It just was perfect timing where he had done a hand design and sort of ported over a lot of what he did. These things right here were directly from his PhD work. So, anyways. All right. Okay. So one other thing that I'm going to just tease you with a bit is transitioning from dexterous manipulation to locomotion, which you can think of as a similar problem, right? Maybe even the same problem, depending on how you want to formulate things. And the same benefits that you can get to having mechanisms passively adapt to the contact for grasping, you can have that same benefit to passively adapt to rough terrain. And so I have a project right now. This was not our latest results, but pretty impressive. Take a look at the body of the robot as this goes. We wanted to design something that kept the robot to be incredibly level passively, right? And so essentially what's happening in some sense is we have two platforms that move with respect to one another, each of which can be statically stable by itself. So there's 4 legs on each. And we let the legs drop essentially and fall on the ground wherever the ground is, right? We don't know where it is. We're just sort of letting them drop and then essentially locking them or applying torque after they're immobilized by contact to support the weight of the robot. And so you can just get a sense of how that works here. Very rough terrain, very different heights. And again, it's feed forward. We're just running this thing through its open loop commands, and it works rather well. Real time, Daniel. All right, so we have a much bigger version of this now that works better and is more, now it's 4x. All right, anyways. Was it 4x the whole time? Did I lie? I didn't see it there. All right. Anyhow, just a couple of plugs here before I finish. Yale has been really growing in robotics. We now have 8 of us, which is pretty impressive. There's only about 100 people in our whole School of Engineering, and we'll be hiring more. There's 4 in computer science, who are the top row there, and 4 of us in mechanical engineering. And so we don't have any open searches now. It would be too late anyways, but probably next year we will, so keep an eye out. I'm also currently at the new Boston Dynamics AI Institute, and we're hiring lots and lots of people. We are getting up to 350 as quickly as possible. So if you have good hands-on skills and are looking for a job, please apply. You don't need a PhD. We're looking for all kinds of people. We're especially in need of perception people, just like everybody, but also maybe somewhat uniquely is we're looking for good mechanical designers. So if you're here because of your interest in mechanical design and you're looking for an internship or a job, please apply. If you do apply, send me an email. It can be to my Yale account if you can't find, I don't think you can find my institute email address, but just let me know so I can flag it and we can keep an eye out for you. So. And then I'm just going to end with my acknowledgments. Lyle here did a lot of the work that was there. But yeah, I'll end there with, and take questions. Thanks.
Right. Thanks, Aaron. We have time for a bunch of questions. So. Yep.
Oh, hi. Thanks for the great talk. So another way to insert sort of compliance and under actuation might be to make the entire finger sort of deformable with like maybe rubber sort of hands or pneumatic. And I was wondering why, what are the advantages of taking like the mechanism route as opposed to sort of being very soft in terms of material properties?
Right. Yeah, I mean, that kind of gets back to the whole F equals KX constraint. That can be fine, you know, in certain situations, but you're really limited due to that relationship in certain ways, right? So if it's a very soft mechanism, it might allow you to make contact very softly, but you're going to be stuck with that K, which is soft, right? And so you're going to continue to be floppy and so forth. So there's, I think in an ideal world, you're very soft and under-constrained before contact, but then after contact, you want to be sort of fully constrained and rigid to be able to apply larger forces, to be able to resist the force of gravity and you know accelerations and so forth. So, so I think that's the sweet spot there.
Thank you.
I'm curious to hear what your thoughts are on like how this scales up in terms of like everything that you talked about is like all about the manipulate or like the hand itself. But I'm curious, what like do you think this could scale up to like the full manipulator arm? And if so, like what sort of like limitations or benefits that you'd see when you do scale the system up?
Right. Come work at the Institute. No, that's actually some of the stuff I'm thinking about doing there is just the idea of how under actuation can benefit for arms and other kinds of things. So yeah, I think yeah, there's a lot of potential advantages just dealing with that over-constraint of the closed loop mechanism. I have not thought about it for very long, so I'm just starting to get ideas on how this might work. I think there's also some benefits for human safety and things. You know, if you bump into something, you can have it sort of passively conform out of the way. But yeah, I don't see why you couldn't have basically the same kind of benefits with arms and legs and so forth.
Thank you so much for the great talk. One thing I was wondering in the initial part of the talk is you said that there's no active sensing or some sort of quote-unquote feedback. So how do you ensure that things that you're trying to pick up would not break, particularly like the wine glass or something?
Right. Yeah, we don't. I mean, yeah, short answer is, but also I think for most things that's not a problem. You know, there's a really not generally always the case, right? But for most things, there's a pretty big range of forces over which you can, you know, be stable and so forth. I mean, grasp force is generally just to resist gravity, and so as long as you can do that, you're stable from the object perspective, and then the breaking it obviously is sort of the other end of the spectrum. So yeah, we're not really taking that all into consideration. There's a bounds over which this works, right? And yeah, I guess I can't think of another word other than ignorant, but the ignorant part of what we're doing is we're ignoring the boundary there. And there's probably a lot you can and should do to think about those kinds of things.
Great, thanks.
Thanks for your nice talk. And I have two questions. And first one is, in under-actuated system, the joint configuration and the actuator configuration is not defined. I mean, the actuator, even I know all the actuator displacements, I cannot know the joint configuration. So in the practical case, I got the issue of even I do same motions for 10 times, then due to the friction and the gravity like that, so the configuration was not exact same even after the 10 times of actuation.
Right.
So how can we deal with this problem? It is one first question. And the second one is, so due to this reason, when we actuate the robot, then the robot configuration is determined by the robot's compliance, in my case. So I mean, if the stiffness of this joint is quite compliant, then it moves first. And if this is stiff, then it does not move like that. So I was curious, how do you determine the compliance of the joint, or the momentum can be also considered? So I think this is quite related to the mechanical intelligence.
Right.
So I was curious about how to deal with this compliance and the momentum like that.
Yeah, yeah.
Thank you.
I'll answer it in reverse. So from the momentum standpoint, we've just kind of been assuming quasi-static for everything, and you know, with at least the stuff we're doing, we're moving slow enough, and the masses are light enough where it hasn't been an issue. Not that it would always not be an issue. Let's see. So the first question was, yeah, how do you know the internal state of the robot with the under actuation? And you don't. You could put encoders, you know, to know what it is. You still can't necessarily control it directly. I would like to be in the situation, ideally, where when you grasp the object, everything is fully constrained. Going back to the you know, softness kind of thing. So in that sense, the entire state of the robot would be determined by the interaction between the hand and the object. So yeah, you could infer it, you know, or you just can put sensors there if you really need to know it. We're doing a lot with just ignoring the hand. Like, I guess one question that I would ask, you know, everybody assumes that you need to know it, but why do you need to know it? You know, if all you really care about is you accomplish the task, that's all you care about. And so, a lot of what we're doing is essentially kind of just ignoring the hand configuration and just looking at the mapping between the actuators and the output object, and we just don't care about the hand configuration itself. And you know, again, this goes into the sort of ignorance direction. Is there are limits, of course, to how well that can work and when that will work, and you'd prefer to know when that is and so forth. But it just works for a lot of situations. So. Yeah, it pushes out of the traditional, you know, knowing everything and planning everything type of approach that we're all sort of as roboticists trained to do. But yeah, it requires a different way of thinking about things, but also enables different kinds of approaches, which are, you know, like the think first and, or, you know, shoot first and ask questions later approach, where we manipulate the object and watch what happens and then come up with a controller with it. You know, that enables you to do a lot of different things. It allows you to deal with problems related to the relative configuration of the object in the hand that's, you know, always difficult to perceive, and you always have to figure that out. And so, yeah. So I would say that maybe you don't need to know it. The other thing is you can get a lot of that stuff with vision, or what you need to know with vision. And that's going to be true of a lot of non-traditional hardware, you know, super soft mechanisms, sloppy, cheap hardware. There's always, you know, a lot of uncertainty between the actuator and your so-called perceived state and what's actually the state. And I think vision will really be able to fill in the gaps there in a lot of ways. Did I miss something? There was something else in the middle that you asked. No?
I think
That was
I
it?
asked two questions, so I
Okay.
think it's done.
All right.
Thank you very much.
Aaron, you pass very quickly through the advantage when you are interacting with, say, a human on under-actuated devices. I think it would be very worth talking a lot about that.
Yeah.
And then I have a silly question.
Okay.
Why do you have when you show like your device, the walking device, why do you have a weight on it?
Oh, that was just because it was unbalanced. We had like all of the, I don't know, the Arduino or something on one side, and we just had to balance it left, right. But that does lead to the whole thing that there is the robot can sort of go uneven if things aren't balanced right. So we are working on that. On the human side of things, yes, I agree. I think it's worth looking at. We took a cursory look at this a while ago, and what I believe we learned was that the most dangerous part about human-robot safety is more of the impact forces that, you know, it's more about the inertia and the velocity of the moving system, and not sure if the under actuation is going to help in that case. I don't think it will. It might be less stiff or something and have some advantages there, but yeah, it's not something I've looked at much, and so I am looking forward to looking at it more. So.
I was thinking more if you use exoskeletal.
Oh, okay, yeah. Right. Let the thing passively fit to the user. Yeah, and that's why, you know, the soft attachment points and stuff are what's used anyways, is to deal with adding additional degrees of freedom essentially. But yes, you run into the problem of you have to then apply forces through those soft contacts, and that is, you know, has limitations to it. So.
In some of the dexterous manipulation example that's showed, I noticed that there's not really much mode changes when you are manipulating the object. I wonder, do you think under-actuated mechanisms are sufficient even for situations where you need to make and break contacts and change contact modes?
Right. Yeah, I'm trying to think if we've done much along those lines. We've done a little bit. We've looked at more high-level modes, not necessarily like contact modes. I mean, certainly if you lose contact, you will often make the mechanism under constraints. And then, you know, in our case, since we do have springs, you'll be in the sort of soft, you know, mechanism role there. But yeah, it's not something we've looked at too much. We've done a little bit, I mean, with the gating, I guess that's a mode change thing. We've done some work with looking at sliding, especially, and so basically, I had a PhD student do his PhD on caging-based manipulation, where we essentially use the hand as kind of like a cage around the object to guarantee that we wouldn't lose it, and leverage that to do things like stuff that's difficult to control, like sliding and rolling on the palm. But yeah, we haven't explicitly looked at a lot of the mode change stuff yet.
Thank you.
Yes.
Maybe to connect to the point, I'm wondering what your thoughts are on hybrid under actuation, where you can turn under actuation on and off. Like, for example, cars have differentials, which are incredibly useful when it comes to driving, you know, on normal streets.
Right.
But for like off-road, you do want to lock your differential.
Yeah, I think there are definitely situations where you would. I mean, like in the situation where you'd lose a contact and gain a degree of freedom, right, then that can create problems. Yeah, I actually have a funny story. I was in the middle of nowhere in Korea bird watching, and there was this like 90-year-old farmer who was out in his little pickup truck, and we were the only people anywhere around. And at some point, he's like walking towards me, and it turns out he like got the truck into a ditch and he couldn't move. So I got in the bed of the truck, and he didn't speak any English, I didn't speak any Korean, of course. I got into the bed of the truck, and I was like bouncing up and down to try to get the thing contacted to the ground and so forth. But yeah, no, I think it would be an interesting thing to think about, locking and unlocking joints and differentials and so forth. So I haven't done it much. You want to do it?
I wanted to start on your first slide.
Are we going through each one individually?
Yeah,
Okay, good.
I have a
I
bunch
didn't know this
of.
was a job talk, but let's go. Sorry.
So you have something on your first slide that says something along the lines of like, good design make things easier.
Right.
Something like
I
that.
probably say everything, which is not
Or
totally
everything.
true, but you know.
So I once said something like that to Russ, and Russ said something along the lines of, whoa, 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 whoa. Wait, are you telling me that you're making your life easier by making my life harder, right? So you're making the design more complicated and in some ways easier to use, but I don't know, maybe it's more difficult to control. I don't know, it has a more complex model. I cannot approximate it by, I don't know, a polynomial, I don't know what it. So I have sort of another way of sort of reading that sentence, which is like, a design is good if it actually makes things easier, right? But I think that
Good design makes Russ's life harder.
there you go. Which I think is a good point, right? So what does it mean to make things easier?
Right.
Or maybe another way, like how do we make sure that it doesn't make other things harder?
Yeah.
I don't know, what are your thoughts on that?
It will make certain things harder. So my first real conference talk, this was like in 2004, and 98% of all of the grasping papers published were grass planning, right? And so I'm sitting in this audience of people who are almost exclusively from a grass planning perspective, and I stand up and I say, my goal is to put all of you out of business. I literally said that. I pissed some people off. Yeah, I mean, not to say Russ is going to go out of fashion necessarily in his approach, but certain things, you know, might not be necessary anymore. It does require and enable, however you want to think about it, a different way of doing things. So, if you really need to know everything about everything, you know, of the state of the robot, or you need to control everything about everything, then it's going to make things harder. I'm thinking about things more from a, you know, very functional task level type of perspective, and I haven't thought about everything, of course, but it does make the acquisition of objects and the passive handling of contacts and those kinds of constraints easier. So it might make Russ's life harder. I don't know. Does it make your life harder, Russ?
Let me channel.
Oh, we're out of
one your-
time. Would you look at the time? It's 4:01.
It's not
I don't
about
know.
control, or how we do control, or if we are stuck on planning. So one of your advisors, Hugh, gave me an example. One time he said, if you want to make people better at climbing, it's really easy. Just put a spring between their hands and their chests. Every time you reach up, they pull up really easily, right? And you're going to spread the work across the push and the pull.
Okay.
And that symmetrizes everything. Climbing is better. But it's really,
I don't know
really
what's going
bad
on
for
with this.
picking up a cup of coffee, right?
Right.
So I think the point is that you can design some of these mechanisms very well for a grasping task, but compliance is going to it reduces your control bandwidth, for instance, right? And it's going to specialize you to some class of tasks.
Right.
Even if I have omniscient control,
Right.
that makes no assumptions about anything. It's really about, what are you baking into the design?
Right. Yeah, I'm not claiming that this is like a universal solution to everything necessarily. It just works really well at some of the basic object acquisition type problems, which are very difficult, and that room full of people, was focusing on optimal placement of frictionless point contacts on a general, you know what I mean? Like, you don't have to do that anymore. So, but maybe you would want to, and this is not the hand for you. So.
Aaron, thank
All
you
right.
so much.
Great,
for that.
thanks.
If you guys have more questions, please bring them to the social event. Food and drinks are over there. Okay. Thanks for joining.